Hello and welcome to this quick NMR review problem. This has an IR spectrum provided and a molecular formula, so I've done some of that preliminary work here, taking this molecular formula provided and determining that it has 5 unsaturations as a result, using the formula for unsaturations. That tells us that there's 5 double bonds or rings or some combination like that. The IR spectrum also shows us that we have a carbonyl stretch visible here. Not a lot of other useful information from the IR, nor do you want to overinterpret IR. I will point out that IR is looking at bonds and behaviors of electrons within bonds, not nuclei, which is NMR, nuclear magnetic resonance. All right, so we have that CO group. We can subtract that from the formula, and this tells us what is left over. Okay, this also provides 1 unsaturation, so there's actually still 4 unsaturations left to describe. Now, as we move down away from the IR, finally to the NMR, we can look at the proton NMR spectrum. We see that by integration, we can count 12 protons distributed along the spectrum. Okay, and then we have in the carbon NMR spectrum 8 peaks, not counting this is a solvent peak, CdCl3 at 77. So this looks like that there's 2 carbons doubled up by equivalence. We can make a very good guess that it's those 2 extra tall carbons. Okay, so we've accounted for our atoms in proton and carbon NMR spectroscopy. Let's look at the proton NMR and let's look at the methyl group here. Why do I know it's a methyl group? Not many other things can integrate for 3 hydrogens. This methyl group is split into a triplet, which indicates that next to that methyl group is a carbon bearing 2 hydrogens. You can look at it as if these 3 hydrogens create 1 signal split 2 additional times to give you a triplet, and that's exactly what we're seeing. So that's the triplet at 1.0 ppm, and these 2 hydrogens are split 3 times, so this is going to be a highly split signal. You would expect that to be a quartet, but we don't see any quartets in the spectrum. We do see what looks like a sextet, 6 lines, if you looked carefully. That would require another CH2 here, and really everything here is CH2s, except for this 1 hydrogen we'll look at in a minute. So this would result in 6 lines, 1, 2, 3, 4, 5, 6, due to the number of neighboring hydrogens splitting this signal. Now, look at the chemical shift here, 4.0 ppm, and the only thing that really can de-shield protons, and probably this carbon as well, that to that extent is an oxygen group, oxygen atom. So if you look at your tables, that can be seen. And so look at all these pieces we have connected together by interpretation of the splitting. So where was our formula where we left off? C9H12O. If we subtract, and that is not the oxygen from the oh, almost gave it away. That's not the oxygen from the carbonyl. It's this oxygen. So we have C3. We can subtract H3, 4, 5, 6, 7, O. Subtract that. What do we have left? C6, H5. Okay. Now let's revisit the carbonyl. The carbonyl is at 190 ppm in the carbon NMR spectrum. Carbonyls are the most de-shielded signals that you'll ever see, most likely. So if you look that up in the carbon NMR table, it suggests very strongly an aldehyde, and you can pretty much believe what you see in that carbon NMR chart for in that region of carbonyl groups. An aldehyde should have an aldehyde hydrogen, characteristically 9 to 10 ppm, and sure enough, there it is. So with those two, we're pretty much certain that we have an aldehyde group. That hydrogen can be subtracted, minus a hydrogen, leaves us with C6H4. And remember, we still have 4 unsaturations left to account for. And so those unsaturations are likely associated with the only signals we have left, and these are in the aromatic region. Could be alkenes, but most likely 7 to 8 ppm, aromatic ring, benzene type aromatic ring, very common in nature, is a good first guess. That's 4 unsaturations. It's C6. Now, we have 4 aromatic protons arranged around this ring in some way. That we can take a look at in a minute. But look closely also at the carbon NMR. Does the carbon NMR verify the aromatic ring? 1, 2, 3, 4, 5, 6 aromatic carbons. So yes, the carbon and the proton are in agreement. If you're on the right track, everything agrees. You're not force-fitting any kind of single piece of data in any way, stretching it in any way to make it fit. We're deriving the structure from the data, not fitting structures to the data. Very important point. Okay, so these 2 hydrogens here, there's some symmetry there. It looks like they're doublets and they're equivalent to hydrogens. So if you draw out all the possibilities, what you'll find very quickly is that the only way to get 2 hydrogens equivalent to each other across a ring like this is some kind of arrangement like this, where it's a di-substituted ring. Substituents like this. So in other words, it's para-di-substituted. What are our substituents? Well, we already have them here, right? So, and it doesn't matter which side they go on. And so we have this molecule pretty much proven at this point. Okay, so what else can we point out? Other key features. These 2 little much shorter carbons. That is typical of quaternary carbons. What are quaternary carbons? Carbons without any hydrogens attached. Those likely are the points of attachment of these 2 substituents. The 164 ppm is got to be the more de-shielded carbon that's attached directly to oxygen. So overall, you want to use a systematic method like this. There's our 4 aromatic hydrogens, nothing left. The other thing you want to keep an eye on are the extra tall carbons, the extra short carbons, obvious signals like a methyl group. You want to also weigh heavily on where carbonyl carbons are in the carbon NMR, associated signals like that, aldehyde proton, or you could, if it was a carboxylic acid, you would see a carboxylic acid proton, very characteristic, very de-shielded, 10 to 13 ppm, and broad, things like that. So the best way is to work multiple problems. I'll have some problems posted on Canvas, extra practice problems if you want to review. The other major take-home message is you cannot avoid knowledge of splitting. As you note, this is the only kind of information we have that actually enabled us to connect these different pieces together. The splitting information. It's the actual only connectivity information. The rest is just lining things up and using logic. So there's more sophisticated NMR methods out there. I'll be teaching that course in the fall, actually. So Thank you.